Welcome everyone. Thanks for coming, and everyone joining online also welcome. So this is what is to be the first talk of the new season, and this is our series of AI Fund with ELLIS invited speaker lecture series, organized by the Center for AI Fundamentals and ELLIS Unit Manchester. Today, it is my great pleasure to introduce Rafael Izbicki. He's based at the Federal University of São Carlos in Brazil. He's visiting us the whole week. Please make a time to talk to Rafael. Rafael did a PhD at Carnegie Mellon University, and today he's going to tell us about simulation-based calibration and so on and so forth. Rafael knows better what he's going to talk about. Floor is yours.
Okay, thanks, Omar. So thanks for the introduction and for inviting me to be here. It's really a pleasure. I've been having a great time. And today I'm going to talk about how we can calibrate confidence and credible sets so that you have good coverage guarantees. And I'm specifically interested about problems which have models that are given by simulators. So I'm going to discuss what I mean in a second. But before I go into the content, okay. So I want just to acknowledge my collaborators from this work. So there are actually 3 papers that I'm presenting more or less here, and they are with different subsets of these people. So Lubin is my current PhD student. He's now coming to INRIA to stay a year. Wagner is my undergrad student. Guilherme was my undergrad student. He's starting his PhD at UCL this year. Mateus was my master student, and he's now at the stats department of University of Washington, getting his PhD. Thiago and Rafael are my colleagues, and Pedro is a researcher at INRIA as well. Okay. So a statistical model is a model that is used to make inference. Well, here I'm using the sense that it's used to make inference about unknown parameters data. So data encode quantities about the world that you can't measure directly, but you'd like to make inference about. And in order to infer data, you observe data X. So the X here is the data that is generated from, that is observed in the real world. And based on this data, you want to go back and constrain data. What are reasonable values of data? And the quantity that links observed data and parameters is the likelihood function, which I'm denoting here by L. So that's the probability of observing the data you've observed as a function of the parameter data. And statistical models, they basically pose a likelihood function. That's what a statistical model is. And based on this model, you can infer data once you observe the data. So there are many methods like maximum likelihood estimation. You can compute posteriors if you're evasions. And these models usually require you to know the likelihood function, or to be able to evaluate the likelihood function at least up to a degree. So most MCMC methods, they require you to be able to evaluate the likelihood function at least up to a constant or something. So you need to be able to evaluate it. But it turns out that in many problems, in many scientific problems, even though you have a statistical model for your data, this model is not simple enough so that you can write down a tractable expression for the likelihood function. So the model is given by a forward simulator. So you can think of a forward simulator as a function that takes data as an input and that outputs X, that is a random draw from the statistical model. And so every time you call this function, even if the input is the same, the output can be different because the model is stochastic. There is some randomness associated to it. So this is a forward model. And the model, it gives you a likelihood function. It's an implicit, there is a likelihood function, but it's very complicated. It's usually a convolution of a convolution of a convolution. You can't compute it even up to a constant. Okay, so people have termed these likelihood-free problems. I don't like the term a lot because it's not that you don't have a likelihood function. It's just that you can't compute it because it's not tractable. But the question then is, how can you make inference in this setting? So you have the observed data, which is the real data, and you can use this forward model in principle as many times as you want. You can call this function as many times as you want with different inputs and get different outputs, the observable data. So you can simulate data sets. How you make inference in these settings, okay? So this kind of model is everywhere. I work with applications in high energy physics and also cosmology, but it appears in many different fields. So one example is n-body simulations, just to make it more concrete. So so there is one standard theory of how the universe evolves. It's called the lambda CDM model. And the lambda CDM model has some parameters, and you want to make inference about those parameters. These are very important parameters. And you can create simulations from the universe. So one example is n-body simulations. You have particles that can be, for instance, stars. They interact with each other in a stochastic way, and you can make the universe evolve in your computer with different configurations of the initial parameters, of these models. And the question is, okay, you can use the simulations. How can you use the simulations to make inference about the observed universe? And one traditional way of doing that is what's called approximate Bayesian computation, ABC. So in ABC, what you try to do is to approximate a posterior distribution. So you have a prior distribution of the parameters, and then you use this forward simulator in a way to approximate posterior distribution. That's, I think, the most standard way of doing that in statistics. This is a good summary of many of the methods that exist in ABC. And the main idea is to use the simulator in this way. So you have a prior distribution over the parameters. This is your likelihood function. And you simulate data in the following way. So first you simulate your parameter vector from the prior. You sample it from the prior. Then you simulate X1 from the forward simulator. So you run the forward simulator with this input data. Then you do the same thing again. You simulate a new independent data from the prior distribution. You run the forward model, and so on and so forth. So you have a large set of simulations with different inputs, different parameter values. And based on this, you approximate the posterior, and ABC methods, are a way of approximating the posterior distribution. More recently, people started to use non-parametric or machine learning methods to estimate the posterior distribution. And the key idea is that the posterior distribution is just the conditional distribution induced by this data generating process of theta given x. That's what the posterior distribution is, the distribution of theta given x on this, induced by this data generating process. And so we did that using a specific method. More recently, people have been using what they call neural estimators, which are neural networks to estimate posterior distributions. So now it's a big thing, of course, to use neural networks to estimate posterior distributions. And you can also estimate, you can do things in a frequentist way by estimating likelihood functions. So I point here. Estimate likelihood functions, you can estimate likelihood ratios and so forth. Okay, so you can estimate different quantities even though you can't compute them, and you use the simulation to estimate them. And what you do with these estimated quantities, one thing which is the focus here is to construct confidence sets. So confidence sets are subsets of the parameter space. Depending on the type of guarantee you want from these sets, they are either confidence sets, which is the frequentist version, or credible sets, which is the Bayesian version. But what we want to do is to construct, get parameter values that are plausible, given the data you've observed. Okay. So, for instance, if you're a Bayesian, you can estimate the posterior distribution using these neural estimators, or ABC, or any other method, or a variational method. You get an estimate of the posterior distribution, and then your confidence set for theta is going to be the set of all thetas such that the estimated posterior distribution is large. Okay, and you can do the same with frequentists. You can use the likelihood ratio statistic. You can use the values, estimated values. But the point is that differently from traditional statistics where you can compute the likelihood function, here you are estimating these quantities that you use to construct these sets. And then the key question is how we calibrate C. How we calibrate C so that you have a good coverage of the confidence sets. So, well, it depends on what you mean by good coverage. So if you're a frequentist, what you typically want to guarantee is that the probability that theta belongs to the confidence set you created is 1 minus alpha for every theta, whichever the true value of the parameter theta is. So this is what's the frequentist coverage. It's conditional on theta, the true value of the parameter. If you're Bayesian, what you typically want is the posterior distribution of the posterior probability of this set to be 1 minus alpha for the data you've observed. So this is the observed data you've measured. So the Bayesian coverage and the frequencies coverage can be seen here in this construction as conditional coverages. One is conditional on theta, the other one is conditional on x. Okay? So, okay, if this is what you want, let's focus on the Bayesian coverage. If this is what you want, what you can do is to pick C so that the posterior probability of this set is 1 minus alpha. But of course, you don't know the posterior probability. You can't compute it because you only have the simulator. But because you estimated the posterior distribution, you can estimate this posterior probability. You already have an estimate of the posterior distribution. That's what comes from the neural network that you fitted to estimate the posterior distribution. So once you have this neural network, you can calibrate C so that the posterior probability of this set under f hat, the true posterior distribution is f hat, is 1 minus alpha. That's what I'm calling self-normalization, self-calibration. Okay, so this is the standard way of picking C. So you calibrate it such that the estimated posterior distribution, it's not P, it's P hat, is 1 minus alpha. Okay. But the problem with this approach is that it doesn't work well in practice. And there are many papers, and this is one of them, showing that, you know, this thing that people have been doing actually leads to really badly calibrated sets. So in this paper, they compared many posterior estimators, like neural posterior estimators with sequential neural likelihood, ABC, many versions of ABC. And what they show is that they yield overconfident posterior approximations, meaning that you have a credible set which has a theoretical probability of having the true parameter, let's say 90%, but it's actually 30%. Okay, so they are overconfident. They think they have the true theta inside it, but it doesn't. Okay, and that's a problem. So how can we? The question we are trying to solve here: can we create other methods that try to improve this calibration in some sense? And the thing is that it's tempting to use conformal prediction to try to calibrate the sets. So conformal prediction, how many of you are aware of what conformal prediction is? Okay, so conformal prediction is an approach for creating prediction sets. So we are in a prediction context. We want to predict a label Y given a feature X. So you don't want to make predictions only. So you don't want to predict, I don't know, what's the height of a person, but you want to give a set with plausible values for the height of that person. So you want to create this prediction set, and you want it to have this coverage guarantee. So the probability that the label of a person belongs to the set you output needs to be larger than 1 minus alpha. And conformal prediction is a way of getting this, even if the model you use to create the prediction set is wrong. So it's a very robust technique in a way. You only assume that the data points are IID, and you have this coverage guarantee, even if the other assumptions you made to construct the confidence set are wrong. So I'm just going to explain quickly what it does. The idea is super simple. You first need to come up with a conformity score. So a conformity score is a measure of how plausible a label value Y is given the feature vector X of your new instance. So, for instance, this is one example of a conformity score. You can create a regression model, a prediction model, G of X, to predict Y given X. So you fit a linear regression or a neural network. And then you say that Y is plausible if this is small, if that Y is very close to your prediction. So that Y is plausible. If this is large, Y is not plausible. You're predicting that the height of a person is 160, but it's actually 190. Okay, so that value 190 is not plausible under this model. So you have to come up with a conformity score. That's one example. Once you have a conformity score, your prediction set is going to have this shape. It's the set of all Ys such that your conformity score is small. Okay, so you're going to include in the confidence set all values of height such that these values of height are close to the prediction you're making using our linear regression, for instance. And but of course, the magic of conformal score is how you choose if they are close enough or not to be included in this prediction set, how you pick C. And the recipe to pick C is simple. You basically compute the conformity score on a holdout set. It's called a calibration set. It's a set that is not used to train the regression model G, the prediction model. So you compute this residual, in this case, on this holdout set, and you compute the 1 minus alpha quantile of the residuals on this holdout set. So you compute, basically in this case, the errors you made on a holdout set that was not used to train. You pick the 1 minus alpha quantile of these errors, and this is how you set C. And if you set C in this way, you can show that the set has this coverage guarantee, even if the prediction model is bad. Okay? So that's the magic of conformal. It's just user ordered statistics. It's very easy to prove that this holds. And we can try to apply that to simulation-based inference. How does it work? So if you remember all the sets I showed you before, they all have this shape of looking at all data that have some measure or some plausibility measure large. Okay, so this is a little bit different from conformal. Here I have small, here I have large, but the idea is the same. So lambda can be an estimated posterior distribution, the likelihood ratio, or the value, or any other statistic. And the prediction, the confidence set we're creating always have this shape, right? Okay, so this is the test statistic in the nomenclature used in statistics, or the conformity score as used in prediction. So it's the same thing, right? It's measuring how plausible theta is given the data X. So theta is Y in this setup, in a sense. Then you can create a data set that comes from the forward simulator the same way as you did to estimate posterior distributions. And then you compute the alpha quantile of these values. So it's alpha instead of 1 minus alpha because it's larger instead of smaller, but the idea is the same. So basically, you compute the test statistic for each element of this simulated data set, and then you pick the alpha quantile. If you do that, and people have done that recently, you get a prediction set that has this nice property. The probability of coverage is 1 minus alpha. So it might look that like the problem is solved. We can calibrate now these confidence sets. But it's not, because the randomness that comes into this probability, well, it has two main sources. There are three, but two main sources. One is the distribution of the data X, but the other one is the prior distribution. What's random here is both theta and X. It's a guarantee that is marginal on the distribution of theta and X. It's the joint distribution of theta. It's integrated. This probability is integrated over the distribution, the joint distribution of theta and X. And that's not what we want. As I said before, we want these conditional coverage guarantees. If you're a frequentist, you want to conditional theta. If you're Bayesian, you want to control coverage conditional on X. And it might look like getting this marginal guarantee, it's at least one step towards getting these conditional guarantees. But it's not. Sometimes you can get closer to marginal guarantees while you get further from these conditional guarantees. So you can show that depending on the test statistic you're using, if you do the naive calibration, it's going to use the self-calibration, it's going to work better in these conditional senses than if you try to conformalize in this global way. You can get further from the conditional control once you want just marginal control. So in this work, we try to improve this. And one way you can try to improve this. Okay, so one important thing. We can't get exact conditional guarantees using distribution-free techniques. So that's a well-known result from the conformal literature. You can't get exact conditional control. So you can't get properties like this for given theta that hold for any, without strong assumptions on the test statistic and the conformity score and the model being correct. So you need to make these strong assumptions. So the best we can hope for is to get asymptotic conditional coverage. And asymptotic here can be in two senses. Either the training set has to be large or the calibration set needs to be large. But in these setups, you can get conditional coverage as n increases. Okay, so you can get marginal coverage, but also hope for asymptotic coverage, and there are conformal approaches that try to do that, and we are going to borrow them into this simulation-based inference problem. Okay. So I just discussed one idea of how that we're going to use to try to control conditional coverage as the sample size increases, which is called partition-based methods or Mondrian conformal prediction. The idea is very simple and smart. It's like this. So we are here in a prediction context. So this is not about simulation-based likelihood-free inference. Okay, we want to predict y given x, and what conformal does is to set a cutoff C that is global. It's the same cutoff that you use whichever x you have. It doesn't look at x. It's the same cutoff everywhere. It's the alpha 1 minus alpha quantile of the residuals, all residuals. So what partition-based methods do is that they partition the feature space, and then you choose a different cutoff for each element of the partition. So you just apply conformal locally. You just look at all samples that fall into that element of the partition, and you compute the 1 minus alpha quantiles among those samples. So you have a different 1 minus alpha quantile here, another one here, another one here, and so on and so forth, for each element of the partition. But of course, this naive approach of partitioning the feature space is usually not good. It works in 1 dimension or 2 dimensions. If you go to higher dimensions, you have the curse of dimensionality, right? Any hyperrectangle you look at in high dimensions is going to have almost no sample points there. Most of them will be empty. So you won't have enough data points to compute these cutoffs, to calibrate the cutoffs. So you have to partition the feature space in a smart way. And to partition the feature space, what we propose in this work, so this is a paper about conformal predictions, not about inference, okay? But we're going to use it here. So what we propose is to partition the feature space using a specific regression tree. And the idea is the following. You can show that the optimal partition groups together points such that the conditional distribution of the conformal score is the same. So even if 2 data points have very different axes, even if they are very far from each other in an Euclidean sense, if they have the same distribution for the conformal score, they should be put into the same element of the partition. So you can show that that's the coarsest way to partition the feature space in such a way that you're going to get conditional coverage. So there are finer ways, but of course you want to be coarse because you don't want to split it too much. Otherwise you won't have enough data points inside each element of the partition. Okay, so the point is, instead of partitioning the feature space in this naive way of just splitting in hyperrectangles, you can try to target this partition because this partition is coarser and still preserves these conditional guarantees asymptotically. So in many setups, this partition is much coarser than the Euclidean one. So just to give one example, if you have irrelevant features, so that's very common for tabular data. You measure many quantities, many variables, and most of the variables are not informative about what you're trying to predict, right? You can show that in this case, you don't have to look at these irrelevant variables when you partition the feature space. You can ignore them. And that's very common. So you have many relevant variables in practical problems. You just can remove them and partition the other part of the feature space, only the variables that are related to the problem. So that's one example. There are many other examples, but of course the question is how we target this partition. We don't know this conditional distribution. But what we do is that we use a regression tree. So it's a regression tree that targets the conformal score. So the output of the regression tree is the conformal score. The input is X. This regression tree partitions the feature space. That's what it does. It partitions the feature space in hyperrectangles with different widths and sizes. And you can show that the regression tree converges to the partition to this partition. Okay. So summarizing what I said so far about this, this is a particular way of partitioning the feature space that is nice, I think, so that you can get conditional coverage. And that's what we did in this paper for prediction. And I'm going to use this technique, something inspired by this, for inference as well, statistical inference. Okay. So summarizing so far, so that you don't get lost because there are many ideas. So our goal is to construct confidence sets that control conditional coverage asymptotically, because that's the best we can hope for. And the tool we're going to use is to adapt conformal methods that control asymptotic coverage. And I showed you one particular method, which is low-cart, that controls conditional coverage asymptotically, which I like. But the specific method we're going to use is going to depend on whether we want frequencies coverages or Bayesian coverage. The details are going to change. Okay. So I'm going to focus on frequencies, confidence sets now, and then briefly discuss the Bayesian ones in the end, because of the time. Okay. So frequencies coverage, we want to control coverage conditional on theta. How do we do that in practice? What we propose, it's the following. So first we simulate a data set from the forward simulator. So theta comes from the prior, X comes from the forward model. We do that many times. We put this data set, huge data set of data sets together. Then we compute for each simulated data set, this pair here, it's parameter and test statistic, parameter, test statistic. So we transform this original data set into this, transform data sets. Then we fit a regression tree. The regression tree is going to take theta as an input and the test statistic as an output. Why theta is the input? It's because we want coverage to be guaranteed given theta, not given X. It's given theta because it's Bayesian, it's frequencies. Okay, so we fit a regression tree. This regression tree is effectively partitioning the parameter space, the space where theta lives. Each leaf of the tree is a different element of the partition. So this is the partition induced by the tree. And then finally, we can tune C using conformal. But instead of using conformal globally, getting the 1 minus alpha quantile over all data points, we just look at the simulated data points that fall into each element of the partition. So we have a cutoff here for A1, a cutoff for A2, a cutoff for A3, a cutoff for A4. We have a local cutoff. And that's how we calibrate our cutoff theta. It depends on which element of the partition theta is on. So that's the procedure we call trust. Then we also have trust plus plus, which is based on forests instead of trees, but the tree is more visual to understand. That's why I showed it here. Okay. Let me know if you have any questions, clarifying questions. Okay, with this method, we can get first local coverage. This is exact. So given that theta belongs to one leaf of the tree, so A here is the element of the partition induced by this tree, one element of the partition, you get exact coverage. So it's still not given theta, right? It's given theta belongs to A, but it's closer to conditional than just looking at marginal, which is not given theta at all. But also we have this asymptotic guarantee. As the number of calibration samples increases, and thus you can grow the tree further and further and make the partition finer and finer, you'll get conditional coverage. Okay, so what I'm increasing here is the calibration sample size. And that's different from traditional statistics guarantees, because traditional asymptotic guarantees in statistics, they are for large sample sizes, observed sample sizes. So when you're doing chi-square approximation to construct confidence sets in statistics, if you're using the likelihood ratio or something like that, what you assume is that the sample size is larger. You have an IID sample of the same data generating process, and under some conditions, this converges to a chi-square. But that's for large n, observed sample size. Here, this can be for small n, okay? And it's asymptotic on the number of simulations, which given enough computational resources, I can increase. It's on my computer. It's not observed data, right? In many of the problems I've worked on, n is 1, actually. It's just one universe. It's like one particle of a muon, I don't know. N is 1. So you can't use the asymptotic statistics, but you can use this. Okay. Yeah.
Just a quick clarification question. So in the setting where n is greater than 1,
yeah.
So you're building a regression from theta to the statistic, but in general, the statistic also depends on X, right?
Yes, yes.
So how would you interpret that? Is that like an average statistic across all your data?
Yeah, that's a good statistic. That's a good statistic. Well, that's a good statistic. It is, but that's a good question. So what you usually do, so let's focus on the posterior. That would be the posterior. Let's see, where's the posterior? Just to give an example. So the question is, what is the statistic? So this would be the posterior of theta given the whole sample. Yeah, and the question is how you estimate it using a neural network. And the way people, have you usually been doing that? How you encode the ID into a neural network? The way people have been doing that is through invariances. So you want the neural network to be invariant over permutations of the inputs. So you can use deep sets to encode that in a neural network. That's what people usually use. That's a good question. If you're just approximating the likelihood, you can approximate the likelihood function of one observation and multiply it many times. Yeah. Another clarifying question? Okay. All right, so that's the method. And I just want to show one quick result. There are many in the paper, but okay, what I'm doing here is basically to apply, to compute many statistics, compare many calibration methods to different setups with different sample sizes and different calibration samples. So N is the calibration sample, B is the calibration sample, and N is the observed sample size, the true data set sample size. And these are setups where the likelihood function is actually known. So I can compute the asymptotic version of the cutoffs, the chi-square approximation. And I'm showing here the number of times, the number of simulations in which each of the method was better. And what's interesting here is that for large sample sizes, observed sample sizes, the asymptotic method does well, right? But for small sample sizes, of course, it doesn't do well because it's asymptotic on the number of samples. But our approaches do better. And we also have Monte Carlo here. You can also use Monte Carlo to solve this problem. But the problem with Monte Carlo is that you have to grid the parameter space. If the parameter space is 1 or 2 or 3 dimensional, you can do that. For more than 3 dimensions, this becomes very, very, very expensive because you have to do this multivariate gridding. So in practice, it needs to be very coarse. And because it's coarse, it doesn't give a good approximation. And in a sense, what our approach is doing is to try to group together theta values that give you the same cutoff. So you are gridding in a sense, but in a smart way. Okay, you can also take other advantages with this tree approach. I'm going to be very quick here because of the time. One of them is that you can think of this conformal set. Well, there is a true C theta that controls conditional coverage, just that we don't know it. And what conformal is doing is to estimate this theta. You can look at this problem this way. But with this partitioning of the parameter space, you can also compute a confidence set for C theta. So you have a confidence set, it's not about theta, it's a confidence set for the true cutoff that controls conditional coverage. So you have a lower bound and an upper bound. And by using this lower bound and upper bound, we can derive uncertainty sets on top of the uncertainty set. So it's a second level uncertainty quantification. So for instance, you can look at all theta values such that the test statistic is larger than the upper bound of your estimated cutoff. These are the ones you're sure to be inside the interval. You can also do the same thing with the lower bound, and then these are the ones you're sure, in a sense, to be outside the interval. The theta is not on the interval. And the ones you are undecided about. The test statistic is between the lower and upper bound for what I think C theta is, so I'm not sure if it's inside or outside the true confidence set. We can do that, and just to show here, this is the kind of thing you get. So if you use standard methods, you get an estimate of the confidence set. This is our estimate of the confidence set. This is a true confidence set. We can compute in this example because we can simulate, because we can compute quantities in this problem. And what you get if you do uncertainty quantification on top of the uncertainty quantification is that you get these regions where, so the dark red points here are the ones we are sure to be inside the interval. The white ones we are sure to be outside the true confidence set that controls conditional coverage, and the salmon ones we are undecided. And I think this plot is very informative, and I think it's the plot I most like about this work, because once I see there are lots of salmon points here, what I can say is that I can't trust the confidence set because I don't know what's happening on these salmon points. But this is useful in practice because it tells me I should increase my calibration sample. Because by increasing this calibration sample, I'm going to shrink the salmon region, which is the uncertainty region due to the simulation. Okay, so I think it's informative. The other thing you can also do that I won't discuss in details is to handle nuisance parameters. So I don't know, most statistical models have many parameters, but you're just interested in a few of them. The other parameters are needed to describe the data generating process, but you only want to construct confidence set for specific parameters that are of interest. You just want to know the mean of the normal. You don't want an estimate of confidence set for the variance. When you have that, it's hard to deal because it's hard to deal with these nuisance parameters if you have many of them. You have to get an infimum over all nuisance parameters. It's very expensive in the traditional way because you are getting an infimum over a large dimensional space, and you don't have an analytical expression for the cutoffs. So you have to grid this nuisance parameter space. But with our construction, because we are using trees to partition the parameter space, the infimum over all values of nuisance parameters becomes the minimum over all leaves of the tree. So that's a much more manageable problem. It's cheap to compute the minimum over a few leaves. I mean, the number of leaves in a tree. It's a finite dimensional space, while minimizing over all nuisance parameters is expensive. So we explored that in the paper, and we show that in practice, it leads to better performance when you have many nuisance parameters. We'll discuss here. Okay, now quickly about Bayesian credible sets. What this changes from what changes here from the frequency sets is that we want to condition on X instead of theta. And so there are two solutions we can use here. The first one is localization, which is the same construction as what we did for frequencies. The only difference is that your regression tree is going to take X as an input instead of theta. Because now we want to partition the feature space and not the parameter space because we want to condition on X and not on theta. But the construction is essentially the same. So that's one version of our method. But there's a second version, which is smart. It's based on this paper, which is not ours. But this paper is about prediction, but we can use the same idea here to do Bayesian coverage in inference. And the idea is what's called rectification. And with rectification, what you do is to start with any conformal score, and then you change it in such a way that with a new conformal score, which I'm calling S prime, so S is the original conformal score, S prime is the second modified conformal score, you get conditional guarantees, even if you're calibrating globally. And the particular transformation that is used in this paper is to compute the cumulative distribution of the conformal score. So this is the CDF of S given X. And you know that the CDF of a random variable evaluated that random variable has a uniform 0-1 distribution. So if you do this construction, the cutoff that controls conditional coverage doesn't depend on X. So you can create a global cutoff, and if the training sample size is large, you are going to get good coverage guarantees. Okay? So that's what they did in this paper. It's a bit challenging in prediction because usually you have a first conformal score, which can be the residual of a regression, like I showed before. But then you have to estimate the cumulative distribution of the conformal score. So you need to estimate this cumulative distribution. You can't compute it. You don't know this distribution. So you have to fit a neural network, a second neural network to do that. In our case, it's a bit easier. Well, it's much easier because in our case, Y's are thetas. And your conformal score, the test statistic, is the posterior distribution. And from the posterior distribution, you have the cumulative distribution of the posterior distribution. It's a function of the posterior. So if the first neural network you created, like your neural network that estimates the posterior distribution, it already gives you an estimate of the distribution of the posterior distribution, which is your conformal score. So in practice, it's easy to do that in the simulation-based inference problem. It's different from prediction. It's much quicker to do, and you have something for free because you already estimated the posterior distribution. In practice, we do that using Monte Carlo. I won't discuss this here. but just to know, for you to know that, you know, there are these two approaches. Localization, which is based on trees, and rectification, it's just a global cutoff, but you change your conformal score. So the guarantees of these methods are different. So localization, which is what I showed before and discussed in the context of inference, is asymptotic, gives asymptotic conditional coverage as the calibration set increases, the set used to pick C. Rectification works as the training set increases, because you need F to be well estimated, the posterior to be well estimated. So depending on whether you believe your estimated posterior, or if you don't, you should choose one method versus the other. I think I'll just show this example. I'm almost done here. Okay, so the oracle cutoff in this example is the black curve. It's the same black curve in all sets, okay? If you do self-calibration, which is the standard way of proceeding with this, you get this, I don't know, which color is this? Salmon curve. Okay, so if you use the estimated posterior to calibrate the cutoffs, this is what you get. It's clearly very far from what you should have. If you use global conformal prediction to improve calibration, you get worse. You see that the region shrinks if you do global prediction, which is what I discussed in the beginning. If you do standard, conformal, globally, you can move further from conditional control. And that's what's happening in practice here. If you use our approach, it really gets wider and gets closer to what you expect, okay? So, you know, global conformal prediction can hurt here in this problem. I think that's important to know, right? We have many experiments in the paper that I won't discuss. So just to finish, so I discussed, I think the main contribution of this work is to link conformal prediction to inference, because that's a question that I see many people asking, whether you could use conformal to make inference, statistical inference, and the link really is that the test statistic, you can see the test statistic as a conformity score. I think that's the new link that is important. And I discussed particular methods you can use when you realize that there's a connection there. What's the connection there? So one is based on trees, the other one is based on this rectification. But I'm pretty sure there are better methods that can be developed. These are the ideas we had, but I think there are other things from conformal that can be borrowed to this inference world, and I think that's the main contribution. But so from a frequency perspective, I think trees are good for localization, because you want these conditional controls, but also because they do uncertainty, they allow for easy uncertainty quantification, and they deal well with nuisance parameters. From a Bayesian perspective, you can be a little bit more flexible because it's easy to deal with nuisance parameters. It's not a nightmare like in frequencies. So you can use localization, but also you can use rectification methods. And I showed one particular rectification methods, but there are others that could be used as well. And just to finish, I want to quickly advertise my book about uncertainty quantification in machine learning. So it's online on my webpage for free. You can also buy it in Amazon. There's a link in the web page. So feel free to download it. And yeah, I hope you like it. So the papers are these ones, the papers directly related to this talk. The first one is about frequencies coverage, and the other one is the second one, which we posted last week, I think, is about Bayesian coverage using conformal. Okay? Thanks a lot.